Hello, this is Jeffrey Frankel with Solutions in Chemistry. Today I'm going to talk about indicators in IB Chemistry HL Paper 1. These are techniques to help you deal with these questions fast and correctly. Many students have a problem with this question and questions of this nature. And the reason may be simply because they don't spend enough time trying to understand what an indicator is. An indicator is simply a weak acid in which the acid part, HIN in this case, has one color, and the anion part, IN-, has the other color. The changeover in color from one to the other takes place at a pH value which is useful in titrations. And let me go through these answers. The correct answer is C. IN- is equal to HIN, the end point of the titration. Let me explain why that is the answer. If you take the concentration of HIN and you make it equal to the concentration of IN-, the cation, you can see that at that point the two colors are mixed, color A and color B. As soon as you add acid to it, you add more H+, it will move in that direction to color A. So you add acid, and this color will start to predominate. HIN will be greater than IN-, and therefore you get color A. If you add alkali, it will take the hydrogen ions away from this reversible equation. Add base in AOH, for example, and you get HIN is less than IN-, and so you get color B. So at the point where HIN and IN- are equal in concentrations, that becomes the end point of the titration. Now, it may be the same as the equivalence point of the titration, and it may not be. Let me show you here. Let's say we have some titration, which is, it doesn't really matter what, that's pH 0 and that's pH 14. And let's say that's a strong one, so it comes down there and it finishes there. If the concentration of HIN and IN- are equal at a particular pH, and this will vary from indicator to indicator, it may be in the range where we want it. Here we want this to be, this is the equivalence point. We know that this is the equivalence point. If we used a probe, we would know that's the equivalence point. And we would want the indicator to change color around about there. Then we can say that is the indicator for this titration. If the indicator changes color around there, it's of no value to us. It's wrong. It wouldn't help us in a titration. And if I go over here and do the other there like that, okay, so that's 0, 14. That's a strong acid, weak base. We want the indicator to change color in that region, not up there. That is no good to us. We want it to change color there. If you're doing a titration with strong acid and strong base, all the way from there down to there, it doesn't really matter where it's there, or there. So that explains why you can have 3 or 4 different indicators will be satisfactory for a strong base and a strong acid. Whereas when it comes to a weak base and a strong acid, only this one will be satisfactory, that won't. And you come over here to a strong base and a weak acid, only that one is satisfactory and that one isn't. Now, the next question is, well, how do you work out what is the pH value at the change. The way to do that is to look at this reversible equation and put it in the form of equilibrium constant. Now, this is an ordinary equilibrium constant. In the case of acid dissociation, which is what that is, or acid ionization, you could call it Ka. But generally, since we're saying it's an indicator, we can call it Kin. And it's equal to this over Hin. At the point where this equals that, then this concentration equals that concentration. We can remove them, and we have Kin equals H plus. And we know that pKin equals minus log Kin, and pH equals minus log H plus concentration. Therefore, pKin equals pH. So if we know the if we know the pK value of this indicator, this acid indicator, this weak acid indicator, we know the pH value at which it changes there or there. Second thing is that the range of change has to be determined by other means. In other words, what I'm just saying that the range of change goes from there to there. It could be much larger. Could be much larger. It depends entirely on the indicator, and that is a different topic which we don't need to be involved in. But this explanation explains why this is the answer to this question. This explanation will help you with other questions in the topic of indicators. This is the reversible equation for an indicator. And in one form it has a colour A, and in the other form it has a colour B. This could be something like phenolphthalein, or it could be something like methyl orange or methyl red, or any one of a range of different indicators. So what's the effect on this acid-base indicator when sodium hydroxide is added? When you add sodium hydroxide solution, it absorbs all of these hydrogen ions and reacts them to form water. So let me give you that. That's H plus plus O, H minus goes to the water. That is strongly on the side of the H2O. Therefore, adding sodium hydroxide pulls the equation to the right, and you'll see more of colour B, and you will not see colour A. So let's see, equilibrium shifts to the right, and more of colour B is seen. Yes, that is the answer. Equilibrium shifts to the left, no, wrong. Equilibrium shifts to the right, more of colour A, no, that's wrong. Equilibrium shifts to the left, no. So the answer here, add sodium hydroxide solution, it absorbs the hydrogen ions, it's a sink for hydrogen ions, and pulls the equation in this direction, pulls the equation to the right. This is another question based on the same equation, the same reversible equation for an indicator. And we know the same thing. In strongly alkaline solution, colour B would be observed. Yes, absolutely. It's the same answer. Strongly alkaline solution, because the alkaline absorbs the hydrogen ion. Strongly acidic solution, colour B would it be observed? No. Ion minus, that's this, is greater than HIN at the equivalence point. No, that's not true. They're actually the same. At the equivalence point, they are actually the same. In a weakly acidic solution, colour B would be observed. No, that's not true. So it's a strongly alkaline solution, colour B would be observed. Yes, simply because all the hydrogen ions are absorbed. When the examiner tells you that an indicator has a pKn of 3.7, he is telling you also that the pH for the colour change is in the same region of 3.7. It may be between 2.5 and 4.5 or thereabouts. This indicator should be used when titrating a known volume of what? Clearly, we know from experience that with a weak acid and a strong base, the pH is greater than 7. With a weak base and a strong acid, the pH is less than 7 at the equivalence point. So we're doing a strong acid and a weak base. And that is where this indicator would be used. Strong acid and a weak base. So if the pKn is low, below 7, then immediately go to a strong acid and say it's a strong acid and a weak base. And that would give you a pH range for the colour change in the same area, below 7. This is clearly the exact opposite of the previous one. In this case, we're dealing with a high pKin of 8.3, and therefore the pH range that it will cover would be in the region of 7 to 10 or thereabouts. For the colour change, the pKin is usually within the middle of the range. This indicator should be used when titrating a known volume of a strong base with a weak acid. Strong base and a weak acid. This is similar to the previous one. Instead of giving you the pK value, it's giving you the pH range. That makes it so much easier. It's clearly we want it to be a strong base. So it's a strong base and a weak acid. That's D. And that's where it will change. Let me do the pH. pH equals 0. pH equals 14. There's 7. Because it's a strong base, you've got that there and there, and it's like this. So it's a weak acid there, going to there, and that. The equivalence point is somewhere where it's greater than 7. So we've got two titrations here we're looking at. One is a strong base and a weak acid. The other one is a weak base and a strong acid. So the question is, which indicator would be best? And for the strong base, we want an indicator which has a high pKin, greater than 7. And for a weak base and a strong acid, we want an indicator which has a low pKin, which is less than 7. So you look through this and you clearly see that C is the answer, indicated with a pKin of 9.6 and an indicated pKin. Some of these questions do require a bit of thinking about, and if you've practiced with them, you will become more fluent at handling this strong base, weak base, strong acid, weak base dichotomy. And it is important for you to just look at the curves that you get from these kind of titrations so that you can handle these kind of questions quickly. In paper 1, they do not require any calculation. In paper 2, you may be asked to do calculations, so you will necessarily have to become competent dealing with pK values, pH values, K values, and hydrogen ion concentrations, and things of that nature. And when I do some paper 2 problems in this area, you will see what I mean. And it does require ability in mathematics, which if you're having problems with, I would suggest you get a textbook on mathematics and work through a few chapters. Look at the chapter on logarithms and work through it. Spend 10 minutes a day for a month playing around with logarithms. And these things, pKa, pH, concentrations, etc., you'll find them easy to deal with. If you found this YouTube video helpful, please subscribe to my channel and look at my other videos. Thank you.